Well, let me see what it's going to be all about. We have these logarithm laws. Yesterday we used them to do some solving with logarithmic equations. Today's going to be all about using the techniques we have to solve some log equations. On the next page, we'll see some quite applied-looking exponential equations appearing. And then on the top page of today's notes, we'll think about combining some ideas we have with some other previous ideas to solve some other equations which will look very exponential, but won't technically be exponential equations. So let's get started in on this. And let's start by just reminding ourselves of the logarithm laws. The log form to x form rule. If someone writes down log base b of x equals y, how could you rewrite that as an exponential?
b to the power of y equals x.
B to the y equals x. And notice, that could be useful if, say, you wanted to solve an equation and all the unknowns were in the thing labeled x right there. If that were the case, then you would have made your life easier. If all the unknowns were in y, then you just make your life worse, but you need to think about what you do before you do it. Or maybe after you do it. Log base b of 1 is... I've heard some mutterings. Someone say something with confidence. 0. Log base b of 1 is always 0. Because b to the power of 0 is 1. Log base b of b is excellent. The logarithm of a product. What's the log base b of x times y?
Log base bx plus log base by.
Cool. So whenever you see a product in a log, you can split it into two logs as a sum. And as we saw last time, it's often useful to go the other way. If you see two logs added together, you can turn them into a single log at a cost of there being a multiplication sign instead of addition. Sometimes that's not too big a price to pay. Sometimes it is. Division becomes
log base b x minus log base b y.
nice. And notice throughout all of these, it's like the base doesn't really matter, but it needs to be consistent throughout. Log base b of x to the y.
Y times log base b x.
Cool. So whenever you see a constant multiplied by a log, you can stick it inside as a power, or the other way around. If you see an exponent inside of a log, you can pull it out as a power. The change of base formula. If you have a base a that you don't like, and you want to write it in terms of log base b, how can you?
Log base bx over log base ba.
Cool. And I know there are some people who have already completed the homework assigned yesterday because there are a few people who tend to get to the homeworks before it's actually technically assigned, which I always find very interesting to see. That formula is quite relevant on that problem, right? The homework assigned on Monday. Wait, what day is today? Friday? The homework assigned yesterday. It's been a week. It's been a semester. It's really useful, we've seen, to write everything in terms of a single log. Sometimes things will cancel if you do. If you have a base for an exponent you don't like, this will be a rule that gets very important and gets lots of use in calculus. You can rewrite it in terms of any other base you like. A to the x is the same as b to the x times log base b of a. And in particular, as you start studying calculus next semester, This will be particularly important for the natural exponential. So the thing I wrote in blue is exactly that. I just took b to be e. Neato. So we have these laws, and we use them to solve some equations. How do people feel about solving logarithmic equations, like the ones written on the bottom half of this page? People feel comfortable, like they could solve any one of these? Anyone feel uncomfortable? Okay. Then, let's proceed as follows. So, let's talk through the first one altogether. And then I'll split you all up into hows to address problems 2 and 3. So let's try to solve that problem 1. Problem 1 obviously being like the simplest looking of the lot of them, right? So if you want to see that equation and wanted to solve it, what seems useful? What seems like a good false move? Yeah, I think I just regularly said something good, but I thought it made worse. Yeah. All of the unknowns are inside of the logarithm, and there's only one logarithm. There's only one log. All unknowns are in the log. So let's write it in exponential form. If you rewrite it in exponential form, let's see, the base is 3 to the power -1 is equal to the thing in the parentheses. Let's see, 3 to the -1 is 1 over 3. That looked like a nicer equation than we had before. In particular, now it's just a linear equation. That look like something you can solve? Yeah, let's go through it. What seems like a good next step? If I want to just like get that x on its own. Let's move the 5 over by, I guess, subtracting it from each side. And maybe in this, well, I got lots of space. So let's add 5 to both sides. 3x equals 1 over 3 plus 5. You know what, before I go through and do the next step, let's carry on simplifying. On the right-hand side, I see a fraction plus 5. What do you need to do whenever you want to add a fraction to a thing and simplify? I guess there are really kind of 2 options here. We could either like just get a decimal approximation, which would be fine. Or if we wanted to write that as a fraction in like reduced form, it would be like, we write that 5 as 15 over 3 and then the whole thing is 16 over 3? Yeah. Oh. That plus became a minus. Thank you. So now I need to subtract a 5 from both sides. So I need to subtract a 5. All right. That error corrected? All right. Now I'll go ahead and get a common denominator, combine those fractions. So that's 1 over 3 minus 15 over 3. That seems like enough space for that column. 3x is equal to negative 14 over 3. You agree? How many people would have probably rounded up instead of writing something like negative 4.66 repeating? Yeah, sure. That's right. Right. It is the same. All right, what do you need to do next? Yeah. Let's divide both sides by 9. X equals negative 14 over 3 over 3. What do you get if you divide by 3 and then divide by 3 again? cut a cake into 3 slices, and I cut each of those slices into 3 slices each, then how many slices are there? 9. So what should I divide by? Good. Everyone was being very quiet. Like, I have trouble judging some things sometimes. -14 over 9, or whatever that is a decimal if you like decimals. That feel pretty okay? Groovy. So, if you ever see a situation where there's just one log, and all the unknowns are inside that log, rewrite your problem in exponential form. And once you rewrite the problem in exponential form, you get a simpler problem. In this case, it was even linear. Should be easier to solve. For the remaining 2 problems, do you see only one logarithm in those problems? Yeah, I see like 3 logs in the second one, and I see 2 separate logs in the first. Do you think you could rewrite those so that there is only one log? Yeah, so maybe I'll give us all 2 options. I can keep talking through one of them and then cut you all loose on the thought maybe. Or I can be quiet and split people up. Do you want me to talk through one of those next examples still? Cool. Which one do you want? Second one. Let's talk through the second one. I guess that is the most complicated looking one because there are like 3 logarithms. And on different sides of the equation. Do they need to be on different sides of the equation though? Could I rewrite this so all the logs are on the same side? Let's rewrite it so all the logs are on the same side. So let's subtract log of 2 from both sides. And you know what? Let's do 2 things in one step. That 2, right now it's like a coefficient, right? Could I move that inside of the log somehow? What would it become if I moved it into the log? Become a power. And 2 isn't so big a power, it's just a square. So, let's do those 2 things at once. So, I see ln of x plus 1. The parentheses do matter because then all of that should be squared. Close parentheses, so I'm now out of the log. Minus ln of x plus 2 minus ln of 2, because I subtracted that from both sides, equals 0. That step make sense? All right. And now it looks like I see 3 logs with some minus signs between them. What does subtraction become if I want to put those all into one log? Division. So let's put, so each of those things that are subtracted will go into the denominator when I write this as a single log. So far, so good? Let's do it. So I will see ln of, and you know what, let's FOIL this bit out while we're at it. X squared plus 2x plus 1, all over x plus 2 from this term times 2 from that term equals 0. Alright, so the stuff inside of the log is looking like a little bit more complicated, but still not so bad. It's a rational function inside of a log, and now there's only one log in this equation. So what's like the stuff you should always do after you get the equation to have only one log? Exponential form. And you'll notice I haven't written this as if there is a base in that log, but what is the base in that log? E. ln means log base E. And if in order to help you just make sense of things, if you need to rewrite your ln's as log base e's, then do it. All right, so you rewrite that in exponential form. The base is e. You know what? Let's not act like I know how much space I'll need. Raised to the power 0 equals the stuff inside the parentheses. X squared plus 2x plus 1 all over x plus 2 times 2. And what is e to the power 0? 1. Oh, so in this problem, did it actually matter what the base was? No, if you had accidentally said, well, e is equal to 17, you would have gotten the same answer. So this becomes 1 is equal to x squared plus 2x plus 1 all over, maybe I'll distribute this 2 through 4x plus 4. 4x plus, nope, 2x plus 4. What am I doing? Take the 2, distribute it through 2x. 2 times 2 is 4. Okay. I made any other errors that I haven't caught yet? Okay. All right. Does that look like an easier equation to solve? In fact, at this stage, does it look like an equation that you just like know how to solve? Yeah, what's like the general outline of how you would attack the rest of this question? I mean, it looks an awful lot like everyone's just like walking, and it's going to just give me an answer if I just pause for long enough, right? Yeah, so maybe let's do that. That looks like an equation you know how to solve. Solve me the rest of this equation. Just tell me what x is. Unless anyone does want me to talk through those details. Okay. Cool. Then I will dot. I'm going to turn off the screen for a second to set something up. People getting down to solutions? Tell me, what are the solutions? Either as exact values or decimal approximations. I hear a square root of 3 as the only solution. Anyone get different solutions? Anyone get themselves stuck at some point and doesn't want me to talk through it? Well, then I'm having a lot of trouble reading the room. So based on that, I'm going to start talking through the solution. I haven't walked this in advance, but like we know what to do. It's a rational equation. So we want to get rid of that denominator. So let's start by getting rid of that denominator. So I'll do some erasing. I'm not saying that the square root of 3 was wrong. I don't know if it's right or wrong. I was just kind of expecting 2 answers because it looks quadratic. So let's get rid of that denominator. 2x plus 4 equals x squared plus 2x plus 1. Oh, okay, yeah, I think I'm beginning to believe that's square root of 3. Maybe there's like a plus or minus. Yeah.
Would we include the negative solution?
Good. Good. So in fact, your answer I think is just totally right, because I think there's an issue with the negative anyway. But like, you should have the plus or minus and then explain why the negative doesn't count. Did everyone actually settle down to like plus or minus root 3? So like going through it would be a waste of time right now, right? Okay, good. That's all I wanted someone to tell me. Dot 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 x equals plus or minus root 3. But now let's check domain. So remember, the square root of 3 is like 1.6-ish? It's somewhere between 1 and 2. 1.76, so 1.8-ish. So let's check plus or minus that and see if it's in the domain. 1.73. So let's think about plus or minus 1.73. If I take plus 1.73 and add 1 to it, is that positive?
Mhm.
If I take negative 1.73-ish and add 1 to it, is that positive? No, because it would be negative 0.73-ish. So the negative one, it doesn't count. If I add 2 to each of those, would they be positive? Yeah, but there needs to be in the domain of both. So the negative 1 doesn't count. So I need x plus 1 to be bigger than 0. So negative root 3 is out. So the solution is x equals square root of 3, or as you said, 1.73-ish. And you know what? The one thing I set up, the thing I said I was running off the screen to do, let's check this. Could we graph this sucker? Yeah, let's graph the original equation. So I'll graph the left-hand side and the right-hand side. The red, I guess, is the left-hand side. Blue is the right-hand side. That look like an x value of about the square root of 3? Cool, I believe it. So, what's the takeaway here? If you want to solve a logarithmic equation, try to change it so that there's only one log involved. Use the logarithm laws to do that. So anytime you see a constant multiple, try to move it in as an exponent. Whenever you see things added together, combine them and it becomes multiplication. Whenever you see things subtracted, find it as subtraction. Obviously, this can make things like really complicated inside the log, but it'll only be like polynomial complicated inside the log. So you can turn that into a rational equation. You know-ish how to solve rational equations. Clear the denominator, and hopefully you don't see like something degree 5. Hopefully you only see degree 2. Feel good? Cool. Is there demand to do one more of this flavor? Cool. Let's do one more of this flavor. Let's address this last one. And I guess the order to do things is like the exact same. How many logs do we see in that equation? 2. That's one more than I would like. I can't rewrite it in log form if there are 2 logs. In fact, there are kind of like 3 logs because one of them has a 2 next to it. So how could I rewrite that so it's an equation that's just log of stuff equals thing? Division looks relevant because there's subtraction, but one other thing I need. What should I do with that too? Move it to the exponent. In fact, do you think I could do like both of those in one step? Yeah, let's do both of those in one step. So this 2 will become a power on top of the x plus 1. This minus sign will become division inside of the log. So what will I get? I will get log base 3. Oh, let's make sure of this. Do all the logs have the same base? Yeah, if you have different bases floating around in your logs, then you might just be in trouble. Log base 3 of x plus 1, parentheses, 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 squared, divided by x plus 2 equals 1. That seem okay? All right. So, was that helpful in just seeing how to rewrite as a single log? Whenever you see a constant multiple, it's going to become a power. Whenever you see addition, it becomes multiplication. Whenever you see subtraction, it becomes division, and then everything's inside of one log. So what's the whole point of writing things so that there's only one log? What's the next thing you should do? Put it in an exponential form. Log base b of stuff equals number. Means b to that number is equal to the stuff. So let's write that down. The base is to the power is equal to stuff. Fair. I'll FOIL out that squaring because I think I'm going to have to anyway at some point. Divided by x plus 2. All right. That looks like an equation you know how to solve? Does it look like an equation that we should spend the time to solve? Should we do? Cool. Solve that as you would any rational function. Maybe I'll write down the laws. Step 1, cross divide. No, it's cross multiply. All right, whenever you see an equation involving a fraction, multiply both sides by the denominator in order to clear that denominator. Next, I guess, get everything to one side. Use the quadratic formula. And finally, check the domain. Because, right, maybe it'll look like there are two solutions according to the quadratic formula, but going from here to there, you've done a bunch of algebra, you may have enlarged the domain. All right, cool. Folks happy with just those steps? Nice. Then, let's go to the next page, where there will be significantly less algebra, and the problems will feel much more applied. The numbers will also be such that calculators will be more or less necessary to get meaningful answers. So, let's talk about radioactive decay. So, here's the left takeaway. If you have some substance that decays radioactively, what that means is that any one of those particles could randomly break apart into some other particles because of some physics, not a physics class. And because there are like lots of particles because they're really small, what that really means is if you just wait long enough that every particle has a 50% chance of decaying, half of the particles will have decayed. So, a lot of times physicists would call it the half-life of a radioactive material. Often denoted with the Greek letter lambda, not for any particular reason, is the amount of time needed for half of that material to decay. Do you think that instead you could record like other lives, like the third life or the seventh life, just as easily? Yeah, you could instead ask, how long does it take for the material to reduce by a factor of 7? That would be the seventh life. One of the Weber problems will ask you to do that. If a radioactive material has half-life lambda, if there was some initial quantity Q0, then at some time t, the remaining quantity is the initial quantity times 2 to the negative t over lambda. And I think I just want to take a moment and convince you that that's a reasonable formula. So every time you go through one half-life, the quantity will divide by 2. So let's say the half-life is 20 minutes. If you wait 40 minutes, how many half-lives have you gone through it? 2. To get that, you divided by the half-life. So this number right here that's just how many half-lives have you gone through. There's a negative sign because I want to divide by 2 that many times. So 2 to the negative. And then you want to start with the initial quantity. So that's why that formula is reasonable for this model. All right, so we have this set up. Let's do something with it. U-232 has a half-life of about 70 years. That's obviously not exact. Nothing's going to be exactly 70 years. How long will it take for a 1 kilogram sample of U-232 to decay it down to 1 gram? So let's write down what this problem is asking and see what we need to do. Do I know the initial quantity for the sample? 1 kilogram. Q0 is 1 kilogram. Do I know how much time I want to wait? No, it asks me when something happens. So I need to solve for t. So I'm going to put more things on that top line. Do I know how much quantity I would like to get down to? 70. So, I don't know, maybe I'll call that TF for the final time. I don't know if I'll stick with that notation. I would like to know when the quantity is down to, wait, 70? 1 gram. You're telling me what the half-life is, which isn't what I asked, I don't think. What's the half-life? 70 years. I need to stop just writing down what people say and think critically about what you said. Solve for t. Let's put some spacing there, make that less funny looking. All right, so let's write down the equation that we get. So the eventual quantity is 1 gram equals, no, the final quantity is 1 gram, equals initial quantity 1 kilogram times 2 to the negative t. I would like to know what t is divided by 70 years. And I've included all the units because I think they kind of matter this time. Because are the units of mass consistent? But are they like close to being consistent? Should I walk in grams or kilograms? Let's walk in grams. What's 1 kilogram? 1,000 grams because of the Latin. And I'm going to keep writing the years next to the 70 because we'll see something interesting happen with the units and how they'll walk out at the end. If you want to drop the years, remember that time is supposed to be measured in years. So, all right. 1 gram is equal to 1,000 grams times 2 to the negative t divided by 70 years. I want to solve for t. What should I do? Well, let's strategize a bit. How many t's do you see in this whole equation? Just one. Whenever you're in a situation where you only see one unknown, just think about everything you do to that unknown and undo it in the opposite order. So it looks like you start with t, you make it negative t divided by 70. Maybe that's all one step, division by 7. Division by negative 70. You put it in the exponent of a 2. Then you multiply that by 1,000 grams. Last thing I did was multiply by 1,000 grams. So what undoes that? Dividing by 1,000 grams. So let's divide both sides by 1,000 grams. So I will see 1 gram. I'm giving myself a little bit of space to the left so that I can put something there. Divided by 1,000 grams is equal to 2 to the negative t divided by 70 years. And what is 1 gram divided by 1,000 grams? Yeah, it's either 1 over 1,000 if you like fractions. If you like decimals, I guess that's 0.001. Which, I don't know. I guess I'll do that. next if we want to get t on its own?
Logarithm.
Yeah, let's apply a log. What log should we apply? What's the base of the exponent in this problem? 2. So I think a log base 2 is useful. So, log base 2 of 0.001 is equal to negative t divided by 70 years. So what next? Let's multiply both sides. I'm going to multiply both sides by negative 70 years, so I can also deal with the minus sign. So it looks like I am getting t is equal to negative 70 times the log base 2 of 0.001 years. People see anything that looks suspicious about that answer? Yeah, there's a negative sign in front anyway. So in order to see if it's actually negative, let's actually have a computer compute that thing and see how negative it actually is. Negative 70 times log base 2 of 0.001. Oh, well maybe it's just, there we go. Is it actually negative? No, because log base 2 of 0.001 is negative already. So you needed an extra negative sign to cancel out that hidden one. So, in fact, we even get a decimal approximation now. We see that it will take about 697 years. Neato. How do people feel about this radioactive decay stuff? So whenever you see something decaying, and you know its half-life, you can use the half-life formula to get a model. You can write down that model and then figure out the thing you need to figure out. Sometimes people, while they were writing out this problem, gesundheit. Like, suppress the units as soon as you could. Just stop writing years. Yeah, not unreasonable. You just need to remember that the end result has to be in years. Cool. So let's do one further application of this. Let's talk about carbon dating. So here is some very rough physics and chemistry setup. The interaction between solar radiation and the atmosphere produces C14, carbon 14. This is a radioactive substance. It's just all over in the atmosphere. As long as you're breathing, eating, and living, you're taking it in. And it's also decaying at the same time. So as long as you're alive, the level of C14 in you is basically the same as what it is in the atmosphere. When you die, assuming that you die, you will stop taking in carbon 14 because you will stop breathing. At that point, you're not taking in any new C14, but the C14 in your body right now is going to continue to decay exponentially. So that means that, if you, dig up a bone, you can say, well, when this bone died, I know how much C14 should have been in it, because it's the same as the concentration that's in the atmosphere. I can measure how much C14 is in it now by doing some sort of chemistry, I don't know. You can then set up an equation and solve to figure out how long this thing had been dead. Assuming you know the half-life of C14, which is apparently about 5,500 years. I've obviously rounded that off because nothing's going to be exactly that. The half-life is some longer number than that. So let's see an example using this. Suppose that you happen to know that when an animal died, it should have had 4 grams of C14 in it. When you dig it up, it has 1/100th of a gram of C14 in it. Is that enough information to figure out how long ago it was alive? Yeah. Let's set up the equation to solve. And then, well, I'll let you solve it, and I'll use a computer numerical technique to solve it at the same time. So, we have the half-life formula. I would like to know how long it would take for the quantity of C14 to reduce to 1/100th of a gram. Do I know the initial quantity? 4 grams, and all the units are consistent, so I'm going to suppress the units. Times 2 to the negative t divided by what's the half-life? All right. Look like something you know how to do. Take a few minutes, solve that equation. I am going to have something separate pulled up once we come back together. Once you get an answer, and maybe you feel reasonably confident in it by maybe comparing with those around you, get yourself a decimal approximation. And once we have that, we will come together and see if this agrees with something we can read from a graph. All right, what do we get? I can only remember like 2 numbers if you tell them to me. Was that the answer people get? Something about that? And in fact, I've already rounded off the half-life pretty savagely, so I don't think I believe more than that many digits anyway. About 47,000 years. Let's also read that from a graph. So, right here, we see the formula for the half-life. Right here, I see the eventual value I wanted to get. Let's just see when they cross. And I expect the answer to be like 47,000, so I've gone out to 50,000 for the input. Look about right. Nice. All right. And I believe I have 5 minutes left on the clock. I think that's enough time to do finish one more example. Let's introduce one more idea that you can use to solve equations. There's an equation. 7 times 2 to the x is equal to pi times 3 to the x plus 1. Does that look like I don't know, does that look like an annoying equation to solve? What looks particularly annoying about it? Yeah, there's like, it's the exponents that make it annoying looking, right? What's the thing that undoes exponents? Logs. So let's see what happens if we hit both sides of this with a log. There's not like a preferred base to use, so I don't think I have a preferred base to use for the log. But let's just pick a log and use it. What log would you like to use? Log base 10. I guess that's the one your calculator does most conveniently. I would say log base e and you do ln, but let's try log base 10. Which means maybe I'll just write log. 7 times 2 to the x is equal to the log of pi times 3 to the x plus 1. All right, so I just hit both sides with a log, and I'm hoping that things become nice on them. And let's see if they do. I see multiplication in each of those logs. What happens to multiplication when you do a log? What happens to multiplication inside a log? It becomes I don't know if the equation looks similar looking now. I guess now there's not multiplication, instead there's addition. That's kind of nice. There's also those exponents, but those exponents are inside a log. What happens when you exponentiate inside a log? It just becomes addition? Cool. So what I see here is the log of 7 plus the log of 2 multiplied by x is equal to the log of pi plus the log of 3 multiplied by x plus 1. All right, so let's just look at what sort of object this is. Log of 7, that's a constant. It's a number. You may be able to tell me about what the log of 7 is, and we could use a calculator to get an approximation. It might even be worthwhile to do. It's a number. So I see a number plus another number times x equals a number plus a number times x plus 1. What's the biggest power you see on any of those x's? 1. This is a linear equation now. I know how to solve linear equations. Try to get all the x's onto one side, all the non-x's onto the other side, and then divide. And perhaps in order to avoid just the complicated looking numbers getting in the way, maybe I'll even say, let's just get some decimal approximations right now. What's the log of 7 about? So this is all going to be approximate, 0.85, plus the log of 2 is about log of pi. .5 plus log of 3. Oh, cool. Now that that's been done, does that look like something that if one had more than negative 42 seconds, one could solve? Cool. In fact, how many people have done already? What'd you get? Oh, okay, I interpreted that as a head nodding. Okay. Cool. Then, we'll come back next time, on Monday. This can be our first priority if people want to ask questions about these. Cool. So, logs that you solve new equations that you couldn't solve before. As a reminder, this afternoon at 3 is this talk that's going to be in board 101, 100, in the email I sent you. Attend that talk, and then come talk to me about it, get some extra credit. So, that you have to talk to me about it is, you have to be attentive during the talk so that you can tell me about it.